I've titled today's presentation, Energy Modeling Optimization, the process of using telemetry to its fullest potential. You know, if we look at the path from telemetry to full energy optimization, modeling optimization, when it comes to the mechanics of how to gather your data, last year's solar car workshop here in January, one of the former Okemos team members came and spoke, and they gave, and you can still see their presentation out, or at least I found it online, that was out there, and it had some great coverage of the specifics of how they did that, and I encourage you to check that out. And I will also say this, each solar car's telemetry hardware specifics are likely going to be unique. Unless you've exactly copied somebody else's hardware, you're likely going to need a little different application because you'll have a different charge controller that either will or will not have some of this data gathering built into it. So just know that that's a little different from car to car. The process that we've used is, and that, you know, all the data you're going to see today, we used Outback Power Systems. So we had their FlexMax 80 charge controller, and they sell a whole set of packet they call like a FlexNet DC, where you can go and gather that data. Now, there's nothing magic about that. Others use Midnight Solar and swear by it. In fact, it could be better than what we have. I just have no experience with it, because we started out down this path some number of years ago. But that's a perfect example of how I could spend all day trying to talk to you about different hardware and we wouldn't cover anything. So we've used the Outback Power Systems, and that's what this data is, but we use this same technique on our advanced car, and we used, when we were doing there, it was an iPanda Galaxy. So it's a Chinese brand, but it had the data gathering inside of it, and we were able to do that. In both cases, we were able to do all these same things. So what is the data you need, and what purpose? Why do you need it? Well, you really need to be able, at the highest level, to do three things. You need to know power consumption relative to speed. So you need to know how much power I'm using right now versus the speed right now, and you need to gather all that data into a database that you can query. You need that. You need solar production. You need to know how much energy I'm making right now and how much am I making relative to right now's global horizontal irradiance. In other words, for the amount of fuel that the sun's sending me right now, how much of that am I converting into power with my array? And you need to know how much, you know, energy is in the battery. How much is in there right now? And it's like knowing how much money is in your checking account. If you have no idea what's in your checking account, you don't know if you're writing hot checks, or if you have enough you could have bought, you know, a little more for lunch. All of this data, we gather it, and the things you're going to see in a moment, we gathered it with 3-second granularity. That's the data granularity that the Outback system pulled it. Once you have that, then you're able to do a full parameterization of your car, as I'll show you later, and then once you have that parameterized, if you have a solar irradiance forecast for today, tomorrow, the next several days, then you can actually develop the optimal speed you ought to be going for the day so that you get the most distance. That's really, at a high level, that's what this is all about, is how to know what speed to go to get the most distance. Don't care about what your competitors are doing and all the pandemonium going on around you. You know what you should be doing, and you go do that, and it'll get you the most that you could possibly get. Okay, so the first year that we were able to really gather data and start to get insights was the 2021 year. This was our 4th year to race. So much of what I'm going to be talking to you about unless you are an insanely skilled first-year team or second-year team, it may take you a few years to get there. There are a few teams that have come in and probably been this far along even the first year, but it's rare. But still, hopefully others are watching this that's been doing it before, and this will also give you something to shoot for as you get there. So for our fourth year, this is the first year we got this data, and I'll start to show you the insight that we got. All right, so this is one of the days out of the fourth year, and I'm going to walk over here a little closer, hopefully not get too far from the mic. But there's a lot of data on here, but this is across the whole day. You can see from 7 in the morning or so all the way through. I think I lost data right around 1640, so right before the end of the race. This is battery voltage across the day against this right-hand axis. So the green is that. The blue is our speed across the day against the right-hand axis. The yellow is our power consumption. This is how much energy we were using instantaneously all throughout the day. And you can tell it's the classic division, so there's a 2-hour break in the middle of the day. And then this is the solar production through the day. A bunch of clouds in the middle of the day. But you can see when we were on tilt in the morning, we're making quite a bit of power. And as soon as we have to put the array off the tilt to flat, we don't make much, like half as much. And then you can see these oscillations up and down. This is every lap around the track. The track is, and so you get different production. And there's even a little shade you go under for a while, going by the signs. And then you can see some clouds right before lunch, then those go away, then we're doing well, then we get into a bunch of clouds, and so on and so forth. It wasn't until after the 2021 race that we took all this data and visualized it for the first time. But we gathered it during the 2021 race. And then as we looked at it, there's a lot, there's many things you could look at on this. If around 44 volts is empty on lead acid batteries, we got to right at empty, maybe even slightly below where we should have been right before lunch. Not terrible. And we got back to the same place right by the end of the day, maybe even slightly below. So we kind of got a lot of what we could have got out of this day. However, there's a lot of things that we could have done in retrospect much better than we did here. Like, if you know that you should be able to go the same, an optimal speed, at least for lunch, and maybe a different optimal speed after lunch, look how terrible we were here. We were like really slow, really fast, slow, fast, or, slow again, way fast, slow. I mean, this is just like chaos. And then in the afternoon, we had a strategy, and guess what? Our strategy wasn't that good, and we got near the end of the day, and we were running out of fuel. We had to really curtail it in order to not run out before the end of the afternoon. So the good news is when I saw this data for the first time, and this took a long time to analyze, but the good news is, going through all this, there's a lot of opportunity to improve. For the same car to get a lot better than we had been. Okay, so take this data. We had 4 days of it. This is the prettiest day. Many other days had more clouds and it's even more chaos. But I took that and we developed regression curves of speed relative to power consumption for each day. So this is the 4 days. And one thing I'll warn you is regressions are only kind of accurate during the relevant range of where they're developed. And so if you have a lot of data points at one speed range, you develop a regression for it, you get some little, odd things like this where it says you use more power to drive slower. That's not true. But most of our speed was in here and in this middle part, and that's where the regressions are the most accurate. So look at this. The first day, we used far more power than we used every single day we drove. We got more energy efficient. Now, one of the things I will also tell you, after the first day, this is back when we still ran a chain drive, Mark helped us add a chain oiler to our chain. And part of getting better in subsequent days, I am convinced, was the less friction of the chain oiler. We subsequently got rid of it because and got rid of the chain and went to a belt drive, which is way better than chain and oil. But look how much more, there's dramatic efficiency gains that occurred. So I think probably half of that was the oiler. But I think maybe more than that, it was each driver getting more efficient, getting more comfortable. And we really preached on we got to get a consistent speed. So moral of the story is we got better with time. This is our team captain, and I took their name. Oh, no, actually, this is, we ended up parsing this out after the fact by the 3 drivers that drove. And we looked at who is most efficient in driving. Now, you'll see this gray one, driver 3, was far more efficient than the other 2. I will say she did not drive until we had already put the oiler on, whereas the other 2 have at least some data in from the time before we put the oiler. But guess what? Driver 3 was the most timid and gentle and everything else, and she was the most efficient. And notice I keep saying she. Our young ladies that drove were almost always the most efficient. There's nothing magic about them being more efficient other than this isn't a hot shot type event. You want to be as judicious as possible, and you see that coming out of this. One other thing we got out of it is first drive included for the student versus not. And what I was trying to show them is there's quite an efficiency gain just getting past your first drive where everything's new and you're getting out here and you're first time in the car, first time on the track, all of these different things. So there's going to be some conclusions we draw from that in a moment. Okay, so after we studied all this 2021 data, the exciting thing that came out of it is that we saw a lot of opportunity to improve. And this is before we even get to full optimization. This is just how to get to where we're much less bad with the same car than we used to be. Now, even though we weren't all that great, we still won first in our division that year, but every year your competition's getting better, every single year. So we knew we had to get better or we would not be able to win the division again. So we ended up kind of finding 3 different areas we could improve. We actually drove 520.8 miles, according to our system that year. And the optimization using the same day's driver regressions, so where we realized we didn't have an oiler the first day, we did the others. So in other words, just the data from that day on power consumption, we saw we could have gotten 1.24% more miles, so 6.5 more miles if we'd just driven the right speed all throughout the time. We found that once we controlled for that and just looked at how the drivers got more efficient each time they drove, if we took that and applied it, there was a 4.76% improvement, or nearly 25 miles that we could have gotten more if the 4th day driver would have been able to be that driver all along. So we saw the lowest hanging fruit is driver training. Get the driver in the car, get used to the car, drive the car to where you don't have jitters, you know what you're doing. And then full day optimization using the 2nd day driving regressions. And this is like trying to optimize across the whole day because, it's a whole day. And if you end up driving really fast in the afternoon, or conversely in the morning, but not in the afternoon because you don't have enough fuel, there's some more gain, and that was another nearly 2 miles. You put all that together, we could have driven another 33.18 miles, same car, same conditions, if we'd fully optimized on all that, nearly 6% more. So it was really encouraging, and we took this, spent a lot of time as a team, talking about it, strategizing on it, and trying to figure out what to do with it. So this is out of the 2021 race, the data gathered, analyzed it, and getting ready for 22. Okay, let me talk to you now about how to parameterize your solar car and how to optimize. Remember I told you earlier we get 3-second granularity out of our telemetry system. What this is, remember I told you also there's 3 areas you need to focus on: power consumption relative to speed, solar production relative to global horizontal radiance, and what's in your battery. This is the first piece. You can see out of, I forget, I don't know if it was 30,000 points. There's a lot of points here. And you look at it and you think, that just looks like chaos. But guess what? It's actually not chaos. There's this red line is a regression. It's a polynomial regression, second order, and somebody might say, well, shouldn't it be third order because aerodynamics go up by the cube of speed, blah, blah, blah. This is the equation that had the lowest R-squared error. And so what it allows us to do is see, as we drive faster, how much power we're using, and this is the equation for it. You can do all this in Excel. Excel will do this. I mean, you can fit a polynomial. It'll develop that for you. And you can try exponential. You can do different things. And you can see by looking at how dark this area is here, a lot of our driving was in the 30-ish miles an hour range. So it's most accurate in that range because that's where most of the data come from. Similarly, we have solar production during the race, race in a flat orientation. And this is showing us what our solar production is relative to Texas Motor Speedway global horizontal irradiance actual data. So let me explain that. There's a weather station on top of Texas Motor Speedway. You can go Google search it, you can find it, and there's years of history out there. And it'll show you, I think it's either 30-second or 1-minute granularity. I forget the exact granularity. We did this some number of years ago. So what we did is we pulled all of our actual solar production out, and we had that in Excel. I think it's 1-minute granularity. We turned the 3-second granularity into 1-minute granularity by averaging the data across the 20 data points for that minute. And then we matched that up to the global horizontal irradiance measured off the Texas Motor Speedway. And we were able to get this data. Now, there's a handful of data points that we actually threw out because our car would be driving under the shadow of one of the big signs. And so it was clearly an outlier. But other than that, this is what came out of that. And I kind of have this array to GHI ratio. Really, the way to think of it is if this says 1.4, that's 1,400 watts. So we were making 1,400 watts when there was 700 GHI out, of global horizontal irradiance. And you notice a couple things. Your actual production relative, well, frankly, just in total, but also relative to GHI is falling as you get higher. You say, well, why is that the case? Why, when there's more fuel from the sun, am I making less power? All of our solar modules that we run are almost, unless somebody's doing something different than us, they're all silicon-based, and those are temperature sensitive. They make less at higher temperatures than they make at lower temperature. And their standard rating for them is usually like 70-something, 78 degrees, I think. Okay, so this gives us this equation. We also, even though I didn't put it in here, we did a similar one for when it's on tilt in the morning and the afternoon, just so that we could see what do we expect to get in the mornings and what do we expect to get in the afternoon. And you can do it, and one of the things we found is if we saw some day-to-day differences. Why? We didn't have our car perfectly perpendicular to the sun. There's some more optimization opportunity. Okay, so once you know that, so we know power, we know production. You notice I didn't talk to you about what's in the battery yet. I'll explain that in a moment. If I try to then go think about if I know what my array will make relative to GHI, how could I use that to think about what I'm going to make today? Well, if you go look at the typically available weather forecast, do you see anything in here about GHI? No, it says sunny, mostly sunny, what the temperature is. So there's nothing useful there to being able to forecast. There's a company, all right, my background is I'm an electrical engineer and I've worked in the power industry for a long time. And with renewable production, whether it be wind or utility scale solar, there's good commercial forecasting companies out there, and this one is called Solcast, that these commercially available forecasting companies, they will tell you GHI throughout the day. In fact, if you'll upload your plant parameters to them, they'll tell you what they think your unit's going to make all throughout the day. We just simply used their GHI. So they will show you, hey, here's what actual GHI has been, 2 days of history. Here's our forecast of GHI through the days ahead. And it's showing you the P50, which is what the dark line is. And it's showing you the P10, which is down here. That means there's a 10% probability it's lower than the P10 number. And then there's a P90 that you can't see that's the same as the P50. So what that's saying is there's either a few clouds or not at all. But look over here, see how the P50 is in the middle and there's a P10 very low and a P90 very high. What this means is there's a huge variation to be expected. There may be a lot of clouds, we don't know. But on a day that looks like this, it tells you there's not a cloud in the sky expected to be coming along. And in a solar car race, this is, this is heyday. This is great. So you can just plug these GHI, and they give it to you in 30-minute increments. I think since then they've added more granularity. But you can either hover over it and it'd tell you, or there's an Excel version of it they'll give you. We just then plug that data. In fact, I'll just show you this next slide where we use it. So once you know that, you should be able to figure out how much energy you're going to make through the rest of the day at all times, between now and the noon break, after the noon break, the whole time. So once you know those things, we just brought this to Excel. And this was our little simple, not that sophisticated, anybody could do this, optimization plan. We've got our speed versus power draw. So this is coming from that polynomial I showed you earlier. And we've got it in a couple of different ways. We got it here just sorted by half-mile increments per hour, what the speed is. Or over here, we have it in watts, to where you can see speed that would go with it. So we'd sit down the night before and we would estimate how much energy is going to be in the battery the next morning. This is back when we had lead-acid batteries. The problem with lead-acid batteries is it's darn hard to know what's in them. What you're going to get out of them varies a lot from time. You could have a full battery, drain the whole thing down, fill it up, drain it down. You could do that 10 times with the same atmospheric conditions, and you're going to get 10 different results. So we were always estimating, and the only way you can estimate is you can only really accurately do that, accurate's a loose term, after the battery's been resting for a number of hours, which really means you can only figure out in the morning, before you charge it at all, how much is in the battery, as best you can tell, and then you got to keep up with what I put in and take out of the battery all day. Now, the good news is there's a way to do that better. But anyway, we would estimate what do we think is going to be in the battery in the morning. We would take the Sawcast forecast, apply it, and figure out what we thought we would make. And then, and this would be what we thought we would make before lunch, because we were trying to figure out in this plan how we're going to drive in the morning for the 4 hours in the morning on the 2022 race. And we would, that would say, all right, between what's going to be in the battery, as best we know, from charging in the afternoon before, what we'll make in the morning, we'll have 6254 watt hours. And then if I divide that by 4, I should have 1563 to work with that morning for 4 hours. Now, at 5:30 in the morning, we'd get up. Before we went over there, we'd go quickly update our forecast because maybe I had some better data. I don't know. Somehow I had the view. I probably had a little more energy. I don't know how I got there. But notice that Sawcast had updated their forecast, and we showed we'd make more power. Altogether, we thought they'd be 1664. So we went into starting our morning thinking we could do 1666. Well, then we get 9:30 or so in the morning. We get out, we get to driving, got a little bit going on. Finally, pay attention to the forecast, update the forecast. And at that point, 6291 is what I thought I'd have to work with. Turns out there's more clouds back in the forecast. So it's saying 1573 is what I'm going to have to work with. You come over here, you work backwards. It says 28.2 miles an hour is what we should be driving to get the most distance that day or that morning. And then you can do the same process by assessing where you think you are right after lunch and for that 2-hour period. So this is how you kind of bring all of that parameterization together. The only weak point of the whole thing is the battery. This is back when we still had lead acid batteries and you didn't really know what was there. It's kind of like only having an idea of how much money is in your checking account versus no idea, but it's not that great. It's better than nothing. Okay, so I've talked to you about how to parameterize all that. You also need a real-time visualization of what's going on. We experimented with different things. This is where we wound up. And it's a pretty, it's something that we had, and it would show us speed in miles per hour, and it showed us 30 minutes, trailing 30 minutes. So all new data is coming on the right, and it's always scrolling right to left. This is showing you our speed that we drove, both instantaneous, and then we did like I think a rolling 30-second average or something to try to smooth it a little. It's showing us battery voltage, how that's going. Now this is the 2023 race when we had moved to lithium-ion batteries. And you can see how voltage is the average and then what it was instantaneous. And then solar current. So both it's showing it in current, but I can, so it's showing me amps, but really power is what I'm focused on. So it's showing me on average over a trailing 30 seconds, what am I making? And then this is motor current, but more important is motor watts. How much am I consuming? And you can see the history of that. Ironically, this stuff's a little noisy. It's a bunch of up and down, but an average is really what you're looking for. And then this last year, 2023, is when the whole plan came together. Once we had lithium-ion batteries and we were able to have a BMS that told us precisely how much energy is in the battery at all times, we were able to pull that into our telemetry. So look at this. It's showing me the battery has 2,685 watt hours. That's sitting right over here. I can see how that is being pulled across time. And then we're able to know I had a plan that's going to have me at a certain level by a certain time. This is how you can track. Are you on plan? Are you above? Or you ahead of plan, below plan, right on plan? This is when it's magic. When you know all those pieces, then you know all you need to know to at all times be thinking about what's the best speed I could be going. And you have to update that because, like all forecasts, reality turns out a little different, but you have all the pieces. Here you can see us. This is the cross-country race. There's that dashboard sitting right there on the laptop, and you can see our car up ahead up here. And we've got all that getting streamed back to us. And you got a plan for the day, but you're constantly sitting there watching. How are you doing? All right. Forgive me, I'm actually proud of this. The pinnacle of our solar car team's energy optimization was this last summer on the leg from Snyder to Carlsbad, New Mexico. And this is at 4:02 p.m. in the afternoon on July 17th. I want to call out to you right here. Energy remaining in the battery, 0 watt hours. The state of charge somehow showed 1%. All right, let's call that a round-off error. That probably was, because I think this only shows in 50 watt-hour granularity. The moral of the story is we ran this battery right smooth down to nothing, essentially nothing left. But for the first time in the history of our team, we had the confidence to go right over to the edge, know precisely where the edge was, and then live there very comfortably. Now you'd say, well, wait a minute, isn't that crazy? Couldn't you have actually, suddenly died? Well, no. We're still making 1,340 something watts. So if you go back to our thing, we should be able to continue to go at a pretty decent speed just off solar alone. However, at this second, we're using 2,000 watts. So when we got to there, if there was another screen print or two later, you're going to see we had to reel it in a little bit and get right back down under the 1,300. So actually, we finished the race with maybe 50 watt hours in the battery. So for the next, because this was at 4:02, there's still more time left. But we were able to hang out right at the battery out empty, knowing we'd got it all, and just keep our speed and power consumption right under what we were making. That's when you know you got all you could get. Well, the good news, put all that together, and we were able to make history for that day and drove the most miles that's ever been driven during this leg of the race. We were able to drive 196.2 miles out of 204.7 optimal miles that day. And I'm confident we could have got the full 204.7, except we had 20 minutes wasted, 10 minutes on a radio problem and something else. Telemetry doesn't fix every problem. But we got 196.2 miles. The prior record for that was 169.2 miles by the Houston Solar race car team in 2018, and that was in the advanced division. So this is showing you how all of this can come together, and once you apply all of these principles to their fullest potential, how you can wring a lot more performance out of your car. For any given car, this energy modeling optimization allows you to get the maximum performance to be extracted from that car. Now, that doesn't mean there isn't 10 other things you could do to make the car more efficient. You should do those things too. But this is how you apply all of that to get the most out of your car. So with that said, if you have questions, I'll be glad, if there are more general questions around energy modeling optimization, I'd be glad to take those now. Unique kind of one-off, how would you do this with your car? We probably ought to take those offline, but I'll give you my contact info there if you want to know. Follow up with me.